All right, we're rolling. Physics 252. I think this is one of the last two remaining full semester courses in physics. So, thanks for being a part of it. How many of you had me online? Just one of you? Face to face? Okay. So you two are not used to me at all? All right. I guess that would be Gage and Devon? Mm-hmm. Okay. I'm Dr. George Fox. So, what do you call, I'm really not real concerned with what you call me. Just, I prefer not Mr. Fox. Mr. Fox is my brother. I have harassed students about that. I know, I came across like a dick, but just not Mr. Fox. My office, you need to get hold of me. Well, if you're here, my office is right through there. Go through that doorway and I'm just to the right, what used to be the storage closet. If you're trying to find my office, you can come up the steps. As you come up the steps, the elevator is right in front of you. You go down the hallway, then go down the next hallway, and the last door on the right, there's a big green dot on my door. And why don't we start out with just a little test? Find out what you know. Yep. All right, so you'll need your own separate sheet of paper. Please do not write on what I'm about to hand to you. This is not for grade. This is just an assessment to figure out what sort of the starting point. If you don't know anything, then, well, it'll show. If you know just as little at the end of the semester, well, that's a problem. But if you don't know anything now, okay, it's not too bad. I've had class average was absolutely horrible, but the standard deviation was also incredibly small. Everybody's starting at the exact same place. So there's a certain convenience to that. Faith, I assume?
Yes.
Good to actually see you face to face.
I know, right?
Yeah, in other situations, I mean, obviously Enrique is gonna help you out there. There's also blank paper up here if it comes to it. So you need a sheet of paper out, and you're gonna do a little assessment, and then when that's done, we'll actually get into stuff and hopefully take you from wherever you are and make you geniuses by the end. I guess genius isn't based upon knowledge, it's based upon ability. Geniuses with knowledge. I am gonna put a 33rd, this is 32 questions, I'm gonna put a 33rd question up on the board, just trying to determine how difficult a problem is. Apparently you're getting the unstable one. I think it's 32 questions. Please don't write this.
Pretty old school those days. Today I just don't have enough paper.
Okay. I can provide you with paper if you would like.
That would be fantastic.
Right, just part of my paranoia on the face masks is that my wife has some comorbidities, as well as we have a boarder who is immunocompromised, and I cannot afford to take coronavirus out. So I ask that you respect that and respect each other and stay masked up. During labs, I'll ask you to wear face shields, which are a pain, but we'll be much closer to each other. And again, not want this to be a super spreader event. All right. Also, for Thursday is lab day. I expect you to print out the lab ahead of time before walking in.
Where is that at? I was kinda looking.
It should be under, when you go to the Blackboard site, there's the menu on the left-hand side. I'm pretty sure I've got a category for labs. You just click on that and it should be the one that's showing with hopefully the right date next to it.
Okay.
Sometimes I'm off a day, so, you know, the one that's close to whatever the Thursday is. Is that sufficient?
I'll leave that
Maybe.
if something happens.
All right, so we'll have a break at some point, and at that point, I can show you on the computer where to find it.
Okay.
And they're due the following Thursday?
Yes. Except when, the next time we have lab, that's when it is. So if there's a test the following week during that lab period, then the lab would be due the week after.
Okay.
But expect it to be due in a week. Any other opening questions? All right, I got one. If you've watched the roadmap video, you know that it ends up at, we start at some relativity and we end up at charge, sort of working backwards. So charge is sort of at the beginning of all of this, so I ask you, what is charge?
Storage of energy. You want the technical definition, I guess?
Technical definition, you need at least 2 charges in order to have energy. You probably could make an argument for it, but then I'd go with what is energy. But any different tag. I'm assuming all of you have had chemistry in some form or another. You dealt with charge in chemistry. Did they tell you what charge was?
Positive electrons.
Say it again?
Positive charge was positive electrons and negative charge was negative electrons. And the positives and negative attract each other. And positives disperse from positives and negatives disperse from negatives.
Okay, so you've defined some properties there. So let's at least get the properties down. You said positive charge with positive electrons?
Yeah, positive electrons.
All right, there are such things as positive electrons, although it's rare from a classroom point of view. I mean, it's a more advanced topic. Anyone happen to know what a negative electron is called?
Positron?
Yes. I think you're thinking of a different particle. What's the most typical, most common positively charged particle?
Proton?
Yes. All right, but you threw in that opposite charges attract. And then conversely, like charges repel. But it seemed like you used the word charge within your definition of charge. Let's try this thing again, didn't it? Probably let students flounder a little bit longer than I should, but charge is not an easy thing to define. There's a reason teachers avoid defining it. They just start talking about it like, of course there's charge. They notice that there's this property of certain objects, particles, that will cause them to repel or attract or neither. And so as they were trying to come up with sort of defining it, they eventually came up with this idea of a positive and negative charge and the fact that opposite charges attract and like charges repel. But what charge exactly is I'm sure there's a theorist out there who feels like he has the answer, but all it is it's a property of particles or objects, I guess ultimately properties of particles which exhibit certain behavior, of which I would consider this rule number one. So there seem to be three types: positive, negative, and neutral. And oftentimes neutral is just, you got the same number of plus as you got minus. The symbol for charge, Q. And I put them both down, not just in case you've never seen the letter Q before. There is a difference between a little q and a big Q. Usually, there is some gray area. Little q tends to be the charge for a single particle. And big Q is for a collection of particles. So when we ramp up the Van der Graaf generator, that would be a big Q because we're looking at the charge of all the net charge over the entire sphere and not just one individual particle. It's net charge of collection.
So, is big Q made of small q or lowercase q?
You can make that argument. I guess mathematically, big Q is equal to sum I 1 to however many you got, little q's behind. Now, I will often use a letter Q. Sometimes I stick to the convention, sometimes I don't. Just be aware that when I write Q, I'm talking about the charge of an object. And so sometimes, just out of bad habit, I will write the wrong Q. It's not, if you put the wrong Q in, you're talking to a group of physicists and you put a big Q and it should have been a little q, or a little q and it should have been a big Q, that's not one of the things they're really gonna get on you about. But textbooks tend to stick to this convention. But again, I've run into a couple of situations where I'm going, ooh, it could go either way. Because technically, proton is a collection of three charges, three smaller charges. But I would still use a lowercase q for a proton. All right, so we got protons and electrons. And what's the third major object within an atom?
Neutron.
I assume you said it.
Neutrons.
Also demonstrating that my hearing is not great. So just speak loudly and clearly, I'll get you. This is too much for physicists to write. There's a whole lot of notation that we will use just because we don't feel like writing words out. So for proton, typically P plus, electrons, E minus, neutrons, and 0. We're not going to do a lot with neutrons because, especially since we're talking about charge here, neutrons aren't contributing a whole lot to that. All right, since all of you have had some chemistry, and presumably at least some of you have had some physics before, I mean, not just 251, but have had at least the basics of this somewhere in your life. What's the charge of a proton?
+1. +1.
Plus one what?
Well, it's just positive in general. And some amount of coulombs, I can't remember what.
Can anyone narrow it down? 10 to the 9 × 10⁻⁴ That's, the typical answer is +1.
Yeah.
In chemistry, that's what they teach you, charge at +1. The charge in terms of actual units that we would use is, so the charge of a proton is 1.6, rounding off, times 10 to the negative 19th coulombs. Now, technically, the unit is lowercase, right there. The symbol is uppercase C. The word coulomb is not a proper noun. Anyone want to take a wild stab at who the coulombs are named after?
Some guy named Cool.
Hey, there you go. Another European. Actually, there's an electric unit called the Franklin, and that would be potentially the first unit named after an American that you would have run across, I think, in these courses. Now, this 1.6 times 10 to the negative 19th coulombs shows up so often. There's a shortcut for that, and so this is often just referred to as E. Not to be confused with the natural log E. So now, we can write in shorthand notation, Q sub E superscript minus negative is equal to negative E. Those two E's do not mean the same thing. So potentially 3 E's that show up in this class. Not the worst case that we run into. The letter mu, at some point we get to magnetism, mu will stand for several things. And you just have to pull from context which mu we're talking about. Mu, as a reminder. One looks like a U with a stem up front. All right, so we've established some ground rules. Anyone know why electrons are negative and protons are positive? And not the other way around?
Because we defined it that way.
More specifically, Franklin. Convention was set in the mid-1700s, and it stuck, and by the time they actually figured out what was going on, they weren't going to change it. I should say, found out what's going on. By the time they had more of a clue about what was going on, they weren't going to change it. Couple other rules to go by. Most of the time, almost all the time, the electrons flow, protons do not. There are two ways that we can move a proton, at least within this room. One way of moving a proton is by actually moving the object, and I just moved a whole bunch of protons there, along with the electrons. I guess in a similar vein, it's similar to that. Later on, I'm going to be charging up one of the rods there, and a little bit of fur is going to come off, and so I'm moving protons there as well. But in terms of electric flow, it's going to be the electrons that move. And way too many students just try to define how an electroscope, one of those things, reacts or why it behaves by a certain way by protons moving from one point to another. I think if you saw the protons moving en masse, the way the student was describing it, you would slowly see this object disappear, which would be a really cool effect, but I suspect we would not survive as a species. And just to throw in a little bit of, we think we know anything. I'm currently reading a book, partway through a book that's title is Electrons Do Not Exist, with the basic premise that we came up with this idea of electrons in order to describe what we're seeing, but again, it is just theory and not definite. That's pretty much true for all science. But with the knowledge that we have here and with the stuff that you do in 251, we can put a man on the moon. So we must be along the right track somewhere. Another rule that electrons flow. It tends to move the path of least resistance. This will become more important when we get into circuits. In chapter, I want to say 29, but that could have been the previous textbook. And I guess the last rule for right now is that charge is conserved. At least the last time I looked, they have not found any exception to this. And the way they would find an exception to it is if there are certain decay processes where suddenly you start out with the positively charged thing and then suddenly what you have afterwards is not adding up to the same amount of charge, then that would be evidence for it. However, you'd have to see that over and over again, and it doesn't seem to happen with the typical particles. I suspect if anything like that happened, you would need, well, a super collider. That's where you get the really strange things. Now, super colliders, you take some particle, at least my dissertation dealt with, we had I think it was a diamond target. They get protons up near the speed of light and then they smash the protons into it and they see what comes out. Super collider just gets them going faster. Closer to the speed of light. Instead of 0.9999 times the speed of light, tack on an extra